So we're going to wrap up our talk on normal distribution by looking at the standard normal distribution today. And why is it a standard normal distribution? So if you just take a peek over here looking at the curve on the right, remember from before, we always have our mean mu in the center, and we can go plus 1 standard deviation, plus 2 standard deviations. We can go mu minus 1 standard deviations, minus 2 standard deviations to create the normal curve. But that mean value could be anything. It could be 1. It could be 17. Our standard deviation could be 0.034. It could be 14.8. So when you're trying to compare two different distributions, it can be a little bit harder to do a good comparison when we have so many different values. So that's why I think it's kind of nice to be able to normalize, right? Where we can kind of not be comparing apples to apples, or apples to oranges, but actually compare apples to apples. So that's the kind of the way I see why we have the standard normal distribution. It just makes it a lot easier to make comparisons. So how do we normalize it? Well, our mean now is going to be 0. And then our standard deviation is going to be 1. So that means no matter what data we're looking at, our average value is now 0. And to go 1 standard deviation over, we're just going to add 1. Right? 2 standard deviations over, we're going to add 2, or going the other way to the left, we can subtract 1, subtract 2, etc. So how can we find these new values? Because like I said before, your original mean could be 47 or 15, right? How do we suddenly make that, or how do we suddenly find what that z value would be? Well, we use this formula. Remembering mu, that lowercase Greek letter mu stands for the mean, right? And then sigma is our standard deviation. And technically sigma is the population standard deviation. I know I mentioned this before, S being sample and sigma being population, but really for our purposes, just remember it's standard deviation. Okay, and X is of course your data value. So once we actually put our values into that formula, we create what we call the z-score. Okay, so the z-score for the X value is calculated using that formula, and it's the number of standard deviations the X value lies above or below the mean. Okay, so what we're going to use is we're going to have to use a z-score table to help us find the probability. So this is where it's kind of nice we can go ahead and reference a resource. It's not something we can actually memorize unless you have an amazing photographic memory. I wouldn't suggest you memorize this. But we can read the table. So if we just take a look at this first bullet point, and I'll show you how to read the table. If we're looking at this, z is less than or equal to negative 1.41. We notice our z-score is negative 1.41. So I'm going to go ahead and switch to my z-score table. And here we go. You're going to notice we have two tables. I have the negative table here, and I'm going to scroll below, and you've got the positive table. So what you see here is basically kind of, if you remember stem and leaf plots sort of thing, you've got basically the ones place and the tenths place of the z value, and then these are your hundredths. So remember we were looking for negative 1.41. So if I'm looking for negative 1.41, I'm going to start here at negative 1.4, but I want the hundredths place to be a 1, so I'm going to look at this value. So to read my z-score table at negative 1.41, I'm going to get 0.0793. Okay, so now going back to our notes, right, that tells us the probability that our z-score is less than, or our z-value is less than or equal to negative 1.41 is 0.0793. Okay. Note, this is always going to be less than, so that's going to be key. We're always looking to the left of the z-score. All right. All right. So what I mean by the probabilities to the left, so again, if you're thinking about your kind of bell curve here, if this is negative 1.41, going to the left is everything this way. So we can only go less than. Okay, so if we look below, what happens if we have a greater than? Because we can totally have a greater than. So if we're looking at Z is greater than, the probability of Z being greater than or equal to 2.47. And then we have to do what's called taking its complement. So remember, everything under the curve is going to add up to 1. So if I do, take a look at this, right? So if everything underneath here adds up to 1, right? So that's equal to 1. And let's say we want some value to the left of that. What I'm going to do is basically take 1 minus this region here on the left. So I don't know if this drawing is helping, but to figure out this region, we're going to do 1 minus that left-hand side. 1 minus the left. So if you look at this example, if we're going to look for Z is greater than or equal to 2.47, let's find that 2.47 first. So going back to my Z-score table, I'm going to scroll down to the positive Z-scores. And we said that was 2.47. So I'm going to read my Z-score. I'm going to start here at 2.4. And then I want the hundredths place to be 7. So if you look up, right, I'm going to go over 1, 2, 3, 4, 5, 6, 7 to get 0.99. Oh, that's not right. I need to go over 8 because that's 0.06. So I'm going to go over to the 8th spot, the 8th column. 0.9932 is the value I'm looking for. So going back to my notes, remember that's 0.9932 here is to the left. That's a 0.9932. So to figure out what's greater than, what we're doing is 1 minus that. So the probability of us actually being higher than that Z-score value is really low. It's 0.0068. So that's what we mean by the complement. It's whatever would, you know, help us sum to 1. So, okay. And then what happens if it's not on our table because our table doesn't show every single value? Well, if you look at the third bullet point, if the Z value is not a number you can find on the table, we'll just approximate the probability. So we have to do our best estimate. So if you look at this next example, if we're trying to find Z is less than or equal to 1.348, well, if you look back at my Z-score table, positive 1.348 is not there because I can only get up to 1.34, right? So here's my 1.34. So going back to our notes, sorry, I keep flipping back and forth, we're going to find those two boundaries. So we can figure out Z is less than 1.34, is what I just showed you earlier. But we can also look at the next one over because 1.348 lies between 1.35 and 1.34. So I have my lower boundary, which is 0.9099. And then if we look at our upper boundary, here at 0.135 is 0.9115. So that's where we get this from. So there's our upper boundary. So we can approximate it to be 0.9112. Now, how do we do that? It's right down here. We're going to add the difference divided by 10 times 8 to get the lower probability, or subtract the difference divided by 10 times 2 for the higher probability. Okay, so let's dig a little bit deeper about why that is how we estimate it, because it's not always going to be like this for every single problem. So let me break it down for you. We can see that 1.348, right, we can add 0.2, or not 0.2, excuse me, 0.002, right, to get to 1.35, or we can take away 0.008 to get to 1.34. So there's how we got the 8 and how we get the 2. Okay, so we add 2 to get to that upper boundary. We subtract the 8 to get to that lower boundary. So that's how I got the 8 and the 2. And then we're going to go ahead and take the difference from those Z-score values, the Z table values, right? So I'm going to take that 0.9115 minus 0.9099 to get, that's going to be 0.0016. Okay, and then what we're going to do with this is we're going to take, this is our difference, and we're going to divide it by 10. And why are we dividing it by 10? Because if you look, our z-score, right, only goes up to the hundredths place, and we want to go to the thousandths place, which is 10 over. So we're going to divide that by 10. That's the way I remember it. So I'm going to take that 0.0016 divided by 10 to get 0.00016. So now we're moving one more zero over, right? Because we want to move this 1.34 to become 1.34 something else, right? 1.348. So we need to get to that thousandths place. So that's why we're dividing by 10. And then you have two options. So option 1, we're going to deal with the lower probability, or option 2, we can deal with the higher probability. So once we have this number, if I want to go lower probability, what I'm going to do is I'm going to take that 0.00016, right, that's the difference, divide by 10. I'm going to multiply it by 8, and I'm going to add it to the lower probability. That's 0.9099. So again, this is the lower probability. Okay, so what I get from that is 0.91118, which, if we're rounding it to the nearest 10 thousandths, right, would be about 0.9112, just being consistent with what the z-score table tells us. Now, if we want to do the upper bound, you can get the higher boundary, right? We can do the second calculation, but we should get the same number. So we're going to take that same difference divided by 10. So this is my higher probability. Take that 0.00016. I'm going to multiply it by 2. And again, why are we multiplying it by 2? Because 2 is what I need to add to 1.348 to get to 1.35. Okay? And then what we want to do is actually take that number and we want to take it away from the higher probability. So let me actually rewrite this so I have a little more space. So we're going to take that higher probability, which is 0.9115, and we're going to take away that 0.00016 times 2. Okay, and that should give us the exact same value. Okay, so if you check your calculator, you should get the same thing I'm getting, 0.91118. What a surprise, right? They're the exact same value, so that's approximately 0.9112. Again, just being consistent with using the same place value as our z-score table. All right, so I know it sounds a little tricky, but the one thing you want to remember is, how do we figure out these values of 8 and 2? It's basically, what do I subtract to get to the lower number? What do I add in that thousandths place to get the higher number? We divide by 10 because we want to think about the thousandths place. And then we either add or subtract depending on which probability you're working with, the lower or the higher. Okay, so let's take a look at a couple more examples, and then hopefully we'll be more comfortable with the z-score table after this. So this example says a study finds that weights of infants at birth are normally distributed. Important, because we can't do the z-score stuff without normal distribution, with a mean of 3,270 grams and a standard deviation of 600 grams. And like I said, don't worry about if it's population or if it's sample. We're just going to use that standard deviation. So some random infant is chosen, and we want to know a couple things. What is the probability that the infant weighs 4,170 grams or less? Less is what we want to work with, because less, right, is to the left. So we want to be less than or equal to. So that means we're going to the left. So that means I can just read my z-score table and be done. Okay? So how do we use our z-scores to actually calculate this? Well, I'm going to scroll back up and remind you guys. We want to first convert or calculate that z-score value. So we're going to use that formula, z equals x minus mu over sigma, which is just saying, our z value, right, is x minus the mean over the standard deviation. So we're going to take our x value right here, which is 4,170, minus the mean divided by 600. Okay, so we can put that into the calculator, and that is going to give us a lovely value of 1.5. Remember, we don't have to deal with that approximation I just went over unless we go past the hundredths place. So 1.5 is in our strike zone. We can just read our table. So what we want to do is we want to figure out the probability that we're at. Okay, so when I put all that in my calculator, I get 1.5, which is awesome. Because remember in our Z-score table, we can go up to the hundredths place. So 10th place is great. It's when we go beyond the hundredths place where we have to do that approximation business I just showed you. Okay, so what does this mean? We want to know the probability that some infant, right, that's our Z value, is less than or equal to 1.5. So let's go ahead and look at our Z-score table to check out that probability. So I'm going to flip back to my Z-score table. I want a positive 1.5. So here's my positive 1.50 because it's to the 10th place. So 0.9332 is that probability. So the probability that the infant weighs 4,170 grams or less is 0.9332. Okay, so for the second part, we want to find the probability that the infant weighs 3,990 grams or more. So the more, right, is where we have one extra thing we have to do because we're looking at, we want to be greater than or equal to 3,990. So we're going to the right here. So what do we have to do? We have to do 1 minus the probability that we are less than that value. So remember, we're looking at the complement. So we still want to start the same way. Figure out your Z value, your Z score. So we're doing our X now, which is 3,990. Sorry, I keep moving. My sleeve keeps touching the screen, so I keep moving things around. 3,990 minus the mean, 3,270, divided by the standard deviation to get that Z score. So that's 1.2. And again, awesome when it's not past the hundredths, we can just read our table. But remember, we're looking for the probability that this baby is going to be greater than or equal to the Z score of 1.2, which is the same thing as 1 minus the probability of Z being less than or equal to 1.2, right? So what we need to do is we can get this off the table. We can't get the greater than from the table, we can get the less than from the table. So let's go ahead and read our Z-scores. So again, we're looking at 1.2 now. So 1.20 is right here, 0.8849. So to calculate this, I'm doing 1 minus 0.8849. So that probability is going to be approximately 0.1151. Right, so just a little bit extra work because we're going to the right. We have to do 1 minus that because our table is always going to tell us the probability to the left. Okay, so we've got some problems, for you to try. Do your best with it, right? One quick heads up before you pause and get to work. This last problem down here about the juniors and the math portion of the SAT, you're going to need to approximate those. So do the best you can with it. And if you do get stuck, feel free to resume the video so you can see my work, but I'll work these out for you guys just to show you again how to do the approximations. But if you want to look back up, right, the approximation was right here with that third bullet point. Think about how I got the lower probability, the upper probability, and then either use that red or the green side, right, to approximate the probability of the Z value. Okay, so again, pause, try it out, and unpause when you're ready to check, or if you get stuck. Okay, so if you're checking that first one, that was pretty straightforward, just plugging it into the formula. So we should get negative 3 1/3. And then for these last two, we went kind of 0 to 60 there. We had to approximate. So remember what we had to do. I'll just look at the first one first. You had to find the Z-score first. So that wasn't very pretty, but we can round it to the nearest thousandths to get our closest approximation. So we're going to get this 2.404, which lies between 2.40 and 2.41, which are on the table. So we've got the lower and the higher. And you can see to go from 2.404 to 2.40, I had to subtract 0.004. So that means we're going to multiply the lower by 4 if we're going to go the route of the lower probability. Or I can see, okay, I have to add 0.006 to get to the higher probability, so I can multiply by 6 if we want to take the green route. But first, we need to find the z-score, the probability from the z-score table, which I got as 0.9918 and 0.9920. Find the difference divided by 10. Okay, then we come back in and you're going to choose either go the red route or the green route, or you can do both to check. It gives you the same number, so regardless of what you want to do. If we're going to lower route, the lower probability is 0.9918 plus the difference divided by 10 times 4. Okay, or if you wanted the higher probability, we take that 0.9920 minus that difference divided by 10, that 0.00002, multiply it by 6. Now, if you looked at the problem, we're doing at least. So this is kind of a combination of all those little things we had to watch out for. So not only do we have to figure out that approximation, which we got as 0.99188, now we have to do 1 minus that because we want to go to the right. We want to go greater than or equal to 76. So we want to subtract that from 1 to get our final answer of 0.0081 approximately. The second part, same approximation, but we didn't have to subtract from 1 because we're looking at most, which is less than or equal to 35. So all we had to do here is calculate your z-score, figure out the boundaries, right? The lower is negative 1.20, the higher is negative 1.19. Then you can see I'm multiplying the lower by 7, the higher by 3. Again, you don't have to do both. Pick one, the other. If you want to do both, it's great to check. But find the difference, divide it by 10, and then you pick, right? Am I going to add the difference times 7, or I'm going to subtract the difference times 3? Regardless of what you do, we get the probability to be about 0.1164. So here I'm just rounding to the nearest 10,000ths to be consistent with our table. So I know that last couple were kind of all the little tricks put together, but hopefully you see how it's done here. But definitely feel free to ask questions if you have any questions on our z-scores. So that wraps up what we're doing with normal distribution. Thank you for listening.